It is 3 in the morning. You ship a minor release for a Go webhook service. The metrics look fine for a minute. Then the graph plunges. For 40 seconds, the cluster silently drops 2% of all incoming traffic. The frustrating part is you did everything right. The deploy was a rolling update. The readiness probes were configured. The YAML was completely valid. The cluster executed your instructions perfectly, and you still dropped requests. That is because running kubectl apply is a request to the scheduler. It is not a deployment design. Fixing this requires stepping back. We have to engineer strict invariants across 3 distinct layers: the container artifact, the cluster execution boundary, and the delivery pipeline. Achieving zero dropped requests requires a deployment design that forces compute capacity and network routing to synchronize perfectly during every state transition. The first invariant is the artifact. The compiled Go binary is the atomic unit of the system, and it must be wrapped in a secure, reproducible boundary before it reaches the cluster. This code shows the first stage of a multi-stage Dockerfile. We use a pinned Alpine Go image as the builder. Copying the go.mod and go.sum files before the source code lets Docker cache the dependency download layer entirely independent of your actual code changes. Down here, setting CGO enabled 0 produces a fully static binary. It removes the libc dependency entirely. We also use the -trim path and -ld flags arguments to strip out build paths and debug symbols, ensuring the build is entirely reproducible. For the second stage, we move the static binary into a distroless runtime environment. Because this image has no shell and no package manager, we eliminate the primary OS-level attack surface. An attacker cannot execute a shell script if the shell does not exist. Compare to a standard Debian Go image. This produces an 18 megabyte artifact. It pulls in under a second and drastically reduces known vulnerability scans. The specific architecture of the container image acts as a primary defense against vulnerability exploits and slow rollback times. With the artifact secured, we hand it to the Kubernetes scheduler via a deployment manifest utilizing a rolling update cytology. This diagram illustrates a rolling update, where maxUnavailable is set to 0 and maxSurge is set to 1. This configuration guarantees cluster compute capacity never drops during a replica transition. The new pod must prove it is ready before an old pod is asked to shut down. But the math breaks down here. When the scheduler kills the old pod, the container receives a SIG-term signal instantly, but the load balancer endpoint update takes time to propagate across the network. If a request hits the old endpoint during that delay, it drops into a void. The solution to this network race condition is mechanical. We use a preStop hook. A preStop hook is an instruction that executes right before the container receives a SIG term. By configuring it to simply sleep for 15 seconds, we force the kubelet to wait. This buys the load balancer the exact time it needs to update its routing tables and drain existing connections safely. Kubernetes YAML is a strict lifecycle contract between your application code and the cluster's network fabric. A pod isolated from network context is still a liability. It requires a default deny boundary to prevent lateral movement if a compromise occurs. This network policy explicitly whitelists traffic. In the ingress block, it only accepts port 8080 from the Nginx namespace. On the egress side, the pod is only permitted port 5432 to Postgres and port 443 for webhooks. Everything else is dropped. Even with strict networking, platform tools like cluster autoscalers routinely drain nodes to optimize infrastructure cost. These automated operations can violate your zero-downtime rollout strategy by evicting too many pods at once. To defend against this, we declare a PodDisruptionBudget. A PDB instructs the cluster API to reject any voluntary node drain that would push the available replicas below our designated threshold. Implementing network policies and pod disruption budgets provides the pod with its own set of enforced constraints against lateral movement and automated evictions. The final layer is the delivery pipeline. This acts as an automated enforcer, blocking unverified artifacts from ever reaching the production cluster. This pipeline illustrates our 7 stages: lint, test, build, scan, sign, push, deploy. Notice the sequence stops at the scan stage. Trivy analyzes the artifact, and if it detects a critical CVE in the base image or dependencies, the pipeline hard fails immediately. Once the image passes the scan, the sign stage uses cosign to cryptographically seal the specific container hash. The Kubernetes admission controller is configured to reject any image lacking this exact signature, preventing malicious overwriting in the registry. We push the artifact, but we do not execute a deploy script. Instead, we use GitOps, where the desired state of production lives strictly in a version-controlled Git repository. A continuous reconciliation tool like Argo CD watches that repository and pulls the changes into the cluster. This turns deployments into pull requests. It forces every configuration change through a peer-reviewed approval gate, replacing human-operated terminal commands with a strict, auditable commit history. A true production pipeline removes human execution from the process entirely. We replace hope with cryptographic verification. This is the complete system architecture. It flows continuously from a secure source code repository through an automated delivery pipeline directly into an isolated Kubernetes ecosystem. We have engineered a lightweight, distroless, multi-stage artifact. We guaranteed compute capacity through maxUnavailable metrics. We mitigated network race conditions using a preStop hook, and we wrapped the delivery in a signed GitOps loop. Every single configuration discussed today is the direct answer to a real production incident. You are looking at the codified lessons of platform teams dealing with system failures at 3 in the morning. Zero-downtime reliability relies on an architecture that enforces stability through verifiable mechanical constraints. This reliability begins in the engineering of these boundaries, long before the first container ever spins up on a node.